So, I will demonstrate the measurement of Hall coefficient as a function of temperature. So, I have already demonstrated how to measure the Hall coefficient as a function of magnetic field or the measurement of Hall voltage as a function of magnetic field. Here basically this we will measure Hall voltage as a function of temperature. So, this is the experimental setup for Hall effect. So, earlier setup whatever I have shown you. So, here also same setup, only we have provision for changing the temperature of the sample, except that one rest of the part here they are same in compared to the earlier setup. So, here you can see this we have a sample, we have placed the sample between the pole pieces of the electromagnet, because Hall effect magnetic field is compulsory, and here we have taken sample p type germanium. As I mentioned that if you have p type semiconductor, then a Hall coefficient, you will get Hall coefficient inversion as a function of temperature, means Hall coefficient will have two contribution, one contribution from the hole and another contribution from the electron. Okay. If hole density is greater than the electron density, then one can see the inversion of the Hall coefficient as a function of temperature. And that is important because we will get 0 Hall coefficient at a particular temperature, and at that point this mu p square p minus mu n square n will be equal to 0. So, from there one can find out the mobility ratio as well as the carrier density ratio. So, in this Hall probe what is that? These are, it looks very compact system, ready-made system. So, this probe here, whatever the sample probe we are using, so there basically we have sample, on sample there are 4 connection, okay, 2 for the current and 2 for the 2 for current and 2 for this Hall voltage measurement, and that probe is placed like this, So, magnetic field will be perpendicular to this, to the surface of the sample. Okay. So, now in this probe we have a heater, then we can heat the sample and we have to measure the corresponding temperature. So, we have also arrangement for the measurement of the temperature. So, basically here we have used thermocouple. So, thermocouple will give us the temperature of the sample. Okay. So, this the box you are seeing, this box everything giving this power is given from this box to the probe. Also it is measuring the temperature as well as the hall voltage. So, basically we have here inside the box what we have here, you can see there is a heater current. Okay. So, heater means this, there is a coil of some probably we use tungsten. So, if you pass current through this coil, then coil will supply heat, and so you have provision to change the heat applying current, more current if you apply. So, heat will be more and temperature will be higher. So, as I told that we will measure the temperature with thermocouple. I will explain what it is. So, basically thermocouple gives the EMF, it is called thermo EMF, and this thermo EMF is the basically voltage. So, here we will be able to see the thermo EMF, and now this thermocouple one has to calibrate temperature versus this thermo EMF. So, this calibration we have calibration chart, company has supplied this calibration chart. So, I will show you, or if it is not supplied, one has to calibrate it. So, this part is for measuring, for heating the sample and measuring the temperature of the sample. Okay. So, other part here, this half is basically, here you can see, now we will set different temperature, and at that temperature what is the hall voltage, and if you know the hall voltage, then corresponding hall coefficient you can calculate. So, what is the, so how to measure the hall voltage? Again this you need this connection, this on sample there are 4 probe, 2 probe and this other 2 perpendicular probe. Okay. So, these 2 probe will be used for setting constant current, and other 2 probe, perpendicular probe, will be used for measuring the hall voltage. So, here you can see this hall voltage, and here it is written probe current. Okay. So, here you have provision for setting probe current, means sample current. So, we will apply a particular probe current or sample current that will be fixed, and then we will apply magnetic field. So, that will be fixed. Now, we will vary the temperature and measure the hall voltage. So, then we will plot hall voltage or hall coefficient as a function of temperature. So, this is the experiment we have to do. So, this part is for temperature, this part is for hall voltage, for hall effect. Okay. So, this part has nothing to do with this hall effect, So, this part is only for setting the temperature of the sample. So, now other part here we have to apply magnetic field. So, this is the electromagnet you have seen many times, and this is the constant current power supply for the electromagnet for this coil of electromagnet. Okay. And then we have to calibrate the electromagnet for different coil current. So, we have to, for a particular air gap, we have to measure the magnetic field using the Gauss meter and Hall probe. So, this is the Gauss meters, and we have Hall probe here, we have Hall probe here. okay, using that one before starting experiment or after experiment, we have to removing the sample, we have to measure the magnetic field as a function of coil current. So, that is the calibration of the electromagnet for a particular air gap, and that we will use for calculating the magnetic field for a particular coil current. Okay. So, that means we will set a particular coil current and corresponding magnetic field we will get from the calibration. So, for that magnetic field and for the sample current, okay, sample current, what is the Hall voltage for different temperature. So, that we will measure. Okay. So, now you see this part I think I have shown you many times. So, so basically these two coils, the power we are giving through this. Okay. So, we can set magnetic field, So, say here I am putting some current, say magnetic field I will use slightly higher magnetic field. Let me apply 4 ampere current. So, 4 ampere current I have set. Okay. So, this is the coil current. Now, what is the magnetic field I do not know. So, that we have to find out from the calibration curve. Okay. So, that after experiment or before experiment one should do that. Since I have already discussed many times. So, I think it is very clear to all of you how to calibrate the electromagnet using the Hall probe and Gauss meter. So, for this, so I have set this coil current means I have set the magnetic field. So, magnetic field is applied on the sample which we want to study. Now, you see I will set here, then probe current I will set. Where is this switch on? I will switch on it. So, probe current I will set here. So, it is already set. So, I think probe current is very high. I should not go to that high. So, probe current 0. So, now I am setting say particular current, it is in millivolt, milliampere here you can see. So, 1 milliampere, let me set 3 milliampere. Okay. Let me set 3 milliampere current, probe current, sample current, okay, that is electromagnet coil current. Now, for that what is the Hall voltage? So, that I can see this in millivolt, it is 48. Now, what is the temperature here? At which temperature this Hall voltage I am getting? So, here I would like to show you, here it is showing this minus 0.14, okay, minus 0.14, but I think there is a procedure here, this thermocouple calibration chart is there, okay. So, which thermocouple here? So, company is telling that chromel alumel thermocouple, okay. So, at different temperature it produce different thermo EMF. So, here temperature is given in degree centigrade. So, 0 degree centigrade. So, the 0 value. So, 1 degree this is 0.04, okay. So, for 2 degree it is up to 9, then 10, 11 up to 19, then 20, 21, 22, 20, 21, 22, 23, okay. So, up to 119 it is given, okay. Now at present the room temperature I have to, so you should use some thermometer, okay, and check what is the room temperature now. So, here it is showing 22.9 degrees centigrade, okay. Now at present the temperature of this room is 23 degrees centigrade. So, now for 23 degrees centigrade, that means here it should be 23 degrees centigrade, it should be 0.92, okay. So, thermo EMF should be 0.92. So, hopefully there is no current, heater current is 0, okay. So, that means I have not applied any heat. So, it is at room temperature. So, I have put at there, and thermo EMF I have to set at 0.92 here, 0.92, 20, 21, 22, 23, 0.92, okay. So, I will set at 0.92. So, I have set at 0.92. So, as per calibration, what is the present temperature? So, that value here thermo EMF we are expecting 0.92. So, I have set it. So, slight change, sometimes it is there, but does not matter much, 0.92, okay. Now, so now I have to note down. at thermo EMF is 0.92, corresponding temperature from the chart it is 23 degrees centigrade, and for that this what is the hall voltage, 47.8. Now, I will change the temperature. So, what I will do? I will put the heater current maximum, okay. Now, temperature will change slowly, it will increase, and this Hall coefficient will change. So, here I will get reading of thermo EMF, and for that thermo EMF what is the Hall voltage. So, just I will note down thermo EMF versus the Hall voltage, okay. And later on there should be one column besides of this thermo EMF. From the chart I will note down the corresponding temperature. So, temperature versus the Hall voltage I will get, and I will be able to calculate Hall coefficient from the Hall voltage, okay. So, let me now give heater current. Generally, how much current I should give? Heater current I am giving now in milliampere. It is, let me give some say 600 milliampere, okay. Say some 600 milliampere heater current. So, for this heater current, so thermo EMF, now I have given arbitrarily some higher current. Now, I will so it will hit the sample and sample temperature will get through the thermocouple. So, I will put thermocouple here. You see, it is from 0.92 it is changing, you see. Now, what I have to do, this also changing, it is not changing much for initial temperature. So, now I have to note down these two reading, you know, I have to note down these two reading. So, I think So, here you can see this from initially it was how much 48. So, now it is a decreasing okay, and this coefficient thermo EMF is increasing, now it is 1.62, it is around 40 degree centigrade, okay. See 1.65, it is basically 41, then 42, then now 1.73, this 43. So, this way temperature is increased. Now, this value is decreasing from 48, it is coming 47.4. So, we have to note down with some step, you have to note down. I think temperature will be higher and higher, this will be decreased faster and faster. So, from here, so Hall coefficient is, Hall voltage is decreasing with temperature. Okay. So, that means Hall coefficient will decrease with temperature. Here it is positive value. So, you will see there is a fluctuation, it happens because yes. So, so here we do not have provision that I think it would be better if we can change the temperature in 5 degree step and then we can wait there and we should stabilize this one, stabilize the temperature, then stabilize the Hall voltage and note down. Okay. But here it is the system is not like this, the system is just continuously heating and so there will be temperature slight change when you are taking this reading. So, it will not be by anyway. So, one can draw graph temperature versus Hall voltage, okay, or corresponding Hall coefficient. So, it is decreasing with temperature. Now, what is the temperature? 2.21, 2.21, 2.21, 2.23, 2.23, temperature is 55. Now, the temperature is around 55. Okay. So, it is a decreasing, okay, with temperature. So, you have to note down as long as it will be 0 and it will go to the negative. So, if you note down that one and plot it, note down and then you plot it. So, we will expect this type of curve, we will expect this type of, this is Hall coefficient and this is temperature. Okay. So, initially you have seen this temperature is increasing. So, here it is plotted, I think during summer they have taken, the students have taken this data. So, it is at 33 degree centigrade, now it is winter. So, it is 23 degree centigrade. So, initially you can see that we saw that Hall voltage is not changing with temperature, because is the same value, no, here it will remain same value. So, that part we have seen. Then after that, after 55, after 50 or 55, it is decreasing sharply, Okay. Now, what is the temperature? Now, temperature is 2.53 thermo EMF, 2.53 thermo EMF. Here you can check 2.51, temperature is 62, okay, 62, and this Hall coefficient it is 40.2. So, from what is the initial value? It is probably how much? 48. So, from there it is changing, this change here I can see, oh, it is a Hall coefficient, one has to calculate the Hall coefficient. So, it is decreasing, coefficient is increasing, means temperature is increasing and the Hall voltage, that means the Hall coefficient is decreasing. Anyway, so here important thing, as I told, it will change like this and then it will cross this 0, it will cross the 0. So, inversion of the Hall coefficient, it will go to the negative, it will go to the negative value, and as I told that we have to take this value, this is Hall coefficient is 0 at which temperature? Here it is showing at 90 degree centigrade, this Hall coefficient is 0. Okay. So, this curve is, since this curve is for this sample, so you will get at 90 degree, we will get at 90 degree this type of inversion, and then you can find out the ratio of the Hall coefficient of, not Hall coefficient, ratio of the mobility, okay, of hole and electron. Okay. So, this is the experiment, So, I will not complete the experiment to show you this inversion, but one can do it. So, this is nice. So, I think I will stop the experiment, but before stopping the experiment, here, as I mentioned here, so this look black box, you know, nothing can be seen. As I told here, for heating arrangement this part is there, here this for Hall effect measurement this part is there. Now one wire is going there, and what is there I do not know. Okay. So, this box, what it is doing, as I told that it is measuring temperature, of the sample. So, sample is here and it is measuring temperature. So, there must be some wire connection for thermocouple, okay, and also heater is there. So, there must be wire connection for heater, as well as there are 4 connection for the Hall measurement, 2 for current and 2 for measuring Hall voltage. So, from here there should be 8 connection, 4 for Hall and 4 for heater and thermocouple. Okay. So, I think I will stop. So, it is decreasing, temperature increasing. What is the temperature now? 2.98, 2.98, 2.98, it's 2.98, 2.97 I can see here. So, temperature is 73. So, at 73 degree centigrade, you have to note down this is the 30.5, Hall voltage 30.5. So, now I will stop it, first I will reduce the heater current. So, heater current I will make it 0, okay. I will make it 0, fine. So, here let it be there, so you can see, now you should see this, it should increase, temperature will decrease again, it should increase, but it is you can just, since it is on, you can just check it, now it is increasing, you see, temperature is decreasing, it is increasing, and this current I will also okay. So, what is there inside of this one? Everything is there, but nothing, you cannot see anything, okay. But here you can see here you can see this 4, this force 2 you are seeing, basically it is giving 4 connection, okay. So, that is a 2 for probe current, means sample current, and 2 for Hall voltage, okay. So, inside there is a sample and these 4 probe connections are there. So, and that wire, this is PCB. So, this on PCB this connection 4 connection they are coming, okay. And here you can see this 8, so other, so this is for Hall connection, and for heater now I can feel heat, when I am touching it I can feel heat. So, there should be 2 more connection for heater and 2 more connection for Hall coefficient. So, here, so I can see this is 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, there are 7, 8 connection, 8 wire connection is coming through this. Okay. So, 4 for Hall, 2 for heater and 2 for thermocouple. Okay. So, and these are all separated wire are coming together and we are putting through this. I can show you. I think probe current I will reduce to 0, probe current I will reduce to 0. Okay. So, let me switch up this one. Okay. So, I will open it, okay. I will open it. So, this type of very convenient connector. So, you can see this hole, this is the female type, this is the female type hole. So, all wires are connected inside. So, female type hole, and this is here you see this male type hole, okay. Here sorry, male type pin. So, pin to hole connection we are making, okay. So, it is called male female connector. So, now here let me open it and show you what is inside. So, I have similar type of same type of, you see I have opened it for you. So, basically I think I will, okay. So, actually what you are seeing, so this is like this. So, some I think I have to take this side, yes, see exactly this, okay. So, this one we are using for just for safety, for holding this, for clamping we are using, you see. So, this same probe I have opened one. So, if you open this, what is there? So, this is just simple cover, okay, for holding the things and for safety covering the things. Now, you see this opposite side, okay. You see the opposite side. So, since inside heater is there, so this is a thermal insulator, okay, as well as electrical insulator. So, I have not opened this one. So, here you can see these two are I do not know whether it is thermocouple or for heater, okay. So, difficult to tell. So, these are the okay, these two it's a looks to me it's a for heater, okay. Inside some coils are there. So, these two are heater. So, you see from here this connection, here is connection. So, PCB. So, these two connections are coming from the heater, okay. These two connections are for heater. This last two coming from these two, this is for heater, okay. So, current is going to the coil, so it is heating. Now, these two are for the thermocouple, okay. So, here you can see these two are for the thermocouple, here this and this for thermocouple. Now, for these 4 for Hall, these 4 connection you can see these 3 are coming, these 3, 1, 2, 3, these 3 and another from here it is coming this. So, this middle 4 basically for this Hall connection, okay, this probe connections, these 4 middle 4, and this side this for heater, and this side these two are for, this side these two are for thermocouple, these two are for thermocouple. Okay. So, using the PCB basically we are, so it is the 4 probe as well as thermocouple and heater. So, this 8 connection from there you see here 1, 2, 3, 4, 5, 6, 7, 8. So, here 8 wires are there, 8 wires are there. So, these 8 wires are coming through this wire, and it is connected with this here whatever holes you are seeing. Okay. So, with that hole, okay, inside there are metallic part. So, there it is connected. Now, this through this we are connecting with this probe here. Okay. Connect with this probe. Okay. So, now here basically what is there here for heating, as I told, this some power supply is there. So, it is applying passing current through this to the heater. Okay. Some power supply is, small power supply is there, and for measuring the thermomef in volts, so some millivoltmeter is there. So, nothing else inside, one millivoltmeter is there and one power supply is there for giving current to the heater. So, some power supply battery kind of things are there. Okay. And here already this part you know this again there are some voltmeter for measuring the hall voltage, and there is a constant current power supply inside also it is there. Okay. So, it is so it this all these 3 voltmeter as well as the current meter means power supply, these are kept inside the box. Okay. If you open this, so one can find out. So, so this is the arrangement, and generally student what they does is a ready made system, just it is somebody put there, make the system ready and just rotating the knob and just taking the reading. But you should understand what are the requirement for the experiment and how you are achieving that that parameters from this instrument. So, that one has to check and clarify. So, this so as I told before the experiment or after the experiment, one has to calibrate the electromagnet, So, put the Hall probe and apply the current, and this is the Gauss meter. Okay. This is the Gauss meter. At present I have put 0 current, so adjust 0, make it, we have to magnetic field is 0. Okay. Magnetic field is 0. Okay. Now, you apply current say apply current and take reading. So, current versus magnetic field you have to calibrate, okay, for different current. So, many times I have done. So, before experiment you should take this reading, that will be the calibration of the electromagnet for this air gap. Now, in case of electromagnet, why company has not supplied the calibration chart as they have supplied for calibration chart for the thermocouple, for the thermocouple thermometer. So, reason is that this chart is only depends on this value of this chart only depends on the type of thermocouple. There are different kind of thermocouple. It's here it is Comel Alumel. So, there are other. So, 2 types of material, 2 wires is taken of 2 materials. Okay. and make the junction of these two wires. So, that junction is put at this at the higher temperature, and other two junction is kept at room temperature. Okay, means it is coming to this to the other two are coming to this voltmeter, which will measure the thermo EMF. Okay. So, induced EMF due to thermal temperature difference between the two end. So, that is why this chart will not change for this thermocouple. So, always it will give this, values. So, it will not depend on any other factors. So, that is why this company has supplied this one and we can use. Okay. But for electromagnet, okay, so it does not depends on the, we are calibrating magnetic field versus the coil current. But this coil this calibration or the magnetic field, it does not depend only on the current, it depends on another part, that is air gap between the magnetic poles. Okay. So, this we cannot keep constant, because using this electromagnet various experiment you can do. So, the sample size will be different. So, you need different air gap. So, you have to change the air gap. So, when you will change the air gap, then for a particular air gap, whatever the calibration curve, that will not be valid. So, that is why company cannot supply the calibration chart for the electromagnet. Student has to or user has to calibrate the electromagnet, keeping the pole gap as desired. Okay. So, I think I will stop here. Thank you for your attention.